So, hello, ladies and gentlemen, to our today webinar, which has the title The 7 Deadly Sins in Engineering Simulation. Let me introduce myself. So, my name is Rolf Salomon from Magna Powertrain here in Austria. I'm responsible for KULI sales for the software KULI. Maybe Christian may mention the software in his presentation a few times, so then you know whom you can contact if you are interested in the software itself. But let me make a few comments to the organization. So you have a button there at the bottom to answer some questions. Please use this function at any time during the presentation. We will answer your questions after the presentation. So we have around 40 minutes for presentation and then 20 minutes for questions and answers. So I think it would be a good possibility to answer your questions at any time and write down in the chat box, and then we will answer this. So, but let's start with the presentation today. So we have the 7 Deadly Sins in Engineering Simulation, which will be held by Christian Rathberger. So who is Christian? So he's a senior manager of vehicle thermal management and KULI software at our company, Magna Engineering Center Steyr here in Austria. He has studied technical mechanics in Linz in Austria, and from 2002 to 2011, he was in the software and method development, plus VTM project applications in KULI. And since 2011, he is the department lead of our department, Vehicle Thermal Management and KULI software. So maybe Christian, now that's your part. Please start with your presentation.
Yeah, Rolf, thank you very much for the kind introduction. So as you can see, I am quite a couple of years now in the engineering business, so to say. And even though I started out as a mathematician, I've now gained quite a bit of practical application also in a lot of customer projects from all around the world. So nevertheless, this kind of seminar to a rather general topic which should address a lot of topics in engineering simulation in general. It is a little bit unusual for me. Normally my topics are very much centered around topics like thermal management, but I think today some of the things that we are about to show will probably and hopefully apply to all kinds of different applications. So generally, why do we think that we have the experience to hold such a kind of seminar? Well, we have basically both me and of course my complete team. We really have a lot of first-hand experience for simulation topics, for engineering simulation topics. So we within Magna, we have to solve engineering questions by simulation on a daily basis. We have more than 20 years experience with doing software trainings for our simulation tool KULI, and we also work in external engineering projects outside Magna, where we, for example, design cooling systems for OEMs, or we optimize cooling systems. We model specific components with a very high level of detail. So we have had quite a bit of chances both to do engineering sins of our own and to also witness other people sinning, so to say. So obviously our experiences are mostly from thermal management simulation, but as you will see in the following, I guess they are fairly universal. So it should also apply to your applications. And I do expect that a couple of the things that I'm about to show you will have encountered yourself from similar application, from similar situations. And nevertheless, you and me, we always keep coming back to some of the sins. Some of these sins happen to all of us, and that's because they are so very, very much tempting. They sometimes look like a shortcut. Well, in the end, usually they are not. And that's my introduction for today's talk about the 7 deadly sins of engineering simulation. All right, so let's start off with the first point. And the first very severe sin that you can make that will always always certainly lead to a lot of pain, probably not deadly sin, but it will be painful in the end. That's when you miss out on data validation, or formulated in a commandment: you shall not base your simulations on garbage, because as the cartoon on the left-hand side shows, as soon as garbage enters your simulation environment in a sufficient amount, almost whatever kind of calculation you do based on it, it will lead to even more garbage. The only possibility where a mathematical operation can be performed on garbage, and it will be a precise number, if you multiply it with 0, and that's not what we usually do in our simulation environments. So obviously everyone knows this, and still mistakes happen. Still people charge forward, enter data that they get from test benches into the simulation environments, kick off simulations, fully trust in the results, and then there is despair following shortly after. So why is that the case? Well, obviously because in most projects there's a lot of time pressure. So sometimes you think, well, why not save the time for validating all the input data? Someone else is responsible anyway. I got this from the test bench guys. If it's wrong, it's their fault. And I can be faster without doing this. And surely you can, at least in the short run. And probably in the end, it's even someone else's responsibility. But still, you will be in the situation where you have to explain why your simulation results have nothing to do with the reality that is experienced in your vehicle or your other component that you're building in hardware at the end of the day. Let me just give you a couple of examples. So what you see here is a heat transfer map for a radiator component in a combustion engine vehicle, or also, in this case, for a combustion engine vehicle. So on the bottom axis, X and Y, you see the airflow on the outside, on the air side. You see the airflow on the coolant side, and represented by the Reynolds number. And on the Z-axis, you see the Nusselt number, which basically tells you how good your heat transfer will be. And if you look at this map, it doesn't look really very much suspicious. Sorry, I was just seeing that actually you don't see here the Reynolds number and the Nusselt number, but actually what you're seeing is the heat transfer, the thermal output in kilowatt. And it looks like a smooth, straightforward map, nothing suspicious about it. But if you take a closer look at this map, and if you translate this test bench data into dimensionless numbers, so if you look at the Reynolds number and if you look at the Nusselt number, then what you see is that these are examples from our simulation tool KULI, that some of the operating points, they do not look quite right. So these bold lines here, these are the measured curves. And what you see is that when the external heat transfer exceeds a certain value, then these numbers start to rise again. These curves, they have a curvature here. For example, if you look at the red line, it climbs here. This might look a little bit strange. Actually, this is not a problem. It just shows that for sufficiently high air flows, the total heat transfer is dominated by the heat transfer on the air side. So this is actually quite okay. But what is not okay is if we compare this to these dotted lines here on the top. These dotted lines, they are the theoretical maximum heat transfer that you can achieve, the theoretical maximum Nusselt number. And what you see is that there are some points which are unphysical. This means that they are not to be expected from the heat exchanger data that we have entered. They do not make sense, and they violate the laws of physics. So it's not that they are unlikely, it is frankly that they are impossible. So what does this mean? Is this a problem? It surely is, because if you look at these lines here, so these are the points where you have high coolant flow rates and very low airflow rates. And these are typically the points that are most critical for a vehicle. This would be, for example, an uphill trailer condition where the airflow is very low because there is hardly any ram air pressure from the air coming from the front of the vehicle. All the airflow has to be generated painstakingly by the fan, and you still want to achieve an optimal thermal performance. And probably, if you do not check this, if you blindly trust on your data, and if you also disregard the warnings that you will most likely get from your simulation tool, you will probably say, okay, my cooling system is well designed also for hill plus trailer conditions. But in reality, you have a much worse performance. In reality, you will have operating points which are way below the dotted line, way below the theoretical maximum heat transfer. And the result will be that even though your simulation models will tell you everything is fine, in reality, some of the customer vehicles at least will overheat when operating in hill plus trailer mode. And how can this be avoided? Well, it can be avoided by checking your input data. Let me give you another example from a slightly different situation. Again, it is, of course, thermal management related, but this is more of an engine topic as such. So here, what you see on the top left side of the slide is an engine test bench schematic. So we have our combustion engine and test bench. We have a preconditioned coolant loop. We have a preconditioned engine oil loop with a couple of heat exchangers and a couple of test positions. 3 test positions marked red for the oil and a couple of additional ones marked in blue for the engine, for the coolant flow. As we will see, it is really important that you have these kind of schematics. So let's now assume that we got some test results, which are now shown on the right-hand side. And the blue line relates to the coolant entry temperature into the engine, and the pink one relates to the coolant exit temperature of the engine. And what we see is that the first couple of points, they look pretty realistic. There will be some heat rejection in the engine, from the engine to the coolant. Accordingly, it will warm up. But then at operating point 7 or so, something strange happens. Suddenly, the temperature information drops to a little bit above 20 degrees Celsius. And even without any detailed analysis, something is very, very strange here. And probably, and we have also, this is of course a generic example, but we have seen very similar things in real life test scenarios. Probably a sensor has fallen out. I mean, it has probably just broken down, or probably it has been shaken loose from the vibration of the running engine on the test bench. Whatever. For one reason or the other, this sensor value drops to a little bit above ambient temperature. So what kind of implications does this create? Well, obviously, if we enter this data in our simulation model straightforward, we will get garbage. Even if the first couple of points are correct, these basically baseline points for the higher operating conditions, they are just not usable. On the other hand, if we check this and if we see that these values are wrong, then we can probably use some of the other measurement positions and identify a realistic heat rejection for the engine from doing some math there. We could, for example, compare the total input and output between the point right after the PFC, the heat exchanger, and after the engine branch. We can do some math. We can work with data anyway. But in order to do so, we need the Testbench schematics, and we need to look at the results. So as to summarize this first point, what do we have to take care for? Well, the most important thing is never blindly trust your test data. And even if it's probably technically not your responsibility, you will be in a lot of trouble if some problems occur. Always validate. And as we have seen in the last example, it does not always have to be some complicated math. You don't need physics all the time. Sometimes a simple visual check, if this looks like you expect it to look, is sufficient to prevent a lot of additional effort and trouble. Always use the support that is offered by a simulation tool. So many tools, including, of course, our simulation tool, KULI, will give you warnings if something unexpected occurs. Don't disregard them. Always try, and this is, of course, something that you will not always get, but try to get accuracy information for the data. Because false data is not always that obvious, obviously. It's sometimes you really have to ensure that you understand, for example, the precision of the sensors that we use during the test. And accordingly, you should really try to get this information from your Testbench engineers. Try to get background information on the Testbench setup for non-standard test scenarios. Yeah, you will need schematics. If you do not know where the measurement positions were, then you are severely restricted in evaluating their plausibility. And ideally, you could even try to get some pictures of the Testbench setup. Maybe one last example before we get to the next one. I once was in a situation with an OEM where they wanted me to calibrate the thermal model for a gearbox based on some thermal imaging data. And they got me very nice videos which showed the temperature distribution on the outside of the gearbox. And I had my simulation model and I tried to calibrate, and it was just impossible to get a reasonable calibration. I was really seriously doubting the validity of my general model, and I did not know what to do. Until I realized that that the videos look a little bit strange. I mean, they looked very plastic, very 3D-like, which was nice. But looking a little bit closer, it was like there is something shining on the external casing of the gearbox, like some reflection. So I talked to my colleague at the OEM and asked him, well, was there something that could have been reflected by the thermal camera? And he said, now that you mention, we had the exhaust pipes running close by. So obviously what I was seeing in my thermal imaging data was not the temperature information of the gearbox, or at least not only, but it was heavily overlaid by reflected thermal radiation from the exhaust pipes. So without this information, obviously, I could not have solved this problem. And it was very decisive. I mean, in the end, it ended up with more trouble because they then tried to put some insulation material on the exhaust pipes, and I didn't hear from them for like 3 weeks. And then when they contacted me again, I said, "What's wrong? Did you make any progress with your test?" And they told me, "Well, sort of. We had a fire at our test bench because we exceeded the temperature limit for the insulation material." So, but anyway, that's not a simulation problem then. Why I'm telling this story is it's always important to learn as much as possible about the test so that you can validate the data that you get. All right, the second sin, extrapolation. You shall not go too far. So as the cartoon on the left-hand side demonstrates, extrapolation doesn't always make sense. Just because you're marrying one day doesn't mean that your wife will have a dozen husbands in a couple of weeks. So by the way, let me just briefly refer to the source for these cartoons. So I'm actually allowed to use them. They're from a homepage called xkcd.com. They're very open with regard to using their images, and I can only recommend going there, because the guy who does these cartoons, he is an engineer himself, or at least I expect him to do so, because he has a very, very suspicious amount of insight into the problems that we encounter day to day. So anyway, you shall not go too far. Well, what can that mean? Let me just give you an example again. If we look at this example here, we see a fairly simple cooling system for a combustion engine passenger car in this case. And specifically, we are looking at the heat exchanger setup, and specifically at the main radiator and the vehicle front end again. So what we see here is in red, this is the data that we have received from the testbed. And we have based our heat exchanger on this data. The operating point we are actually evaluating is somewhere else. It is, as shown here, this green dot. It is far outside the original test data. So there are now some possibilities. Either the investigated operating point is wrong, which it probably isn't, or the test data for our heat exchanger is severely lacking. And you will still get a simulation result with this. But the question is, how much will it be worth? Because I have shown here in blue and in black two very different heat exchangers, which are both identical in our available test data area. So they are 100% the same in the data that we have, but they differ greatly outside. And the message is, your simulation tool cannot predict which one will be the right one. It will just try to use whatever kind of physical property it has available to extrapolate. It will, if there are no physical properties available, it will just try to extrapolate based on the gradient and gradient, or maybe some other assumptions, but it will be an extrapolation. And in reality, having the identical set of data in this red area, having only data from there, does not allow us to predict which heat exchanger is the actual one. And this can have, again, severe implications, because we are actually simulating a temperature level of 97.7 degrees Celsius, which is still below 100 degrees Celsius and probably safe for our application. On the other hand, if we were on our heat exchanger number 1, we would expect a coolant temperature of around 99 degrees Celsius, which is still pretty close. Usually the test data is always not 100% precise. There will be slight deviations also based on the built-in situation and the application of your models. So this is probably okay. It's still below 100 degrees Celsius. But if we look at the blue heat exchanger, which has a significantly lower thermal output, this means that we need a higher coolant temperature level to remove the heat from our cooling system. And we will get coolant temperatures of 105 degrees Celsius plus. So probably this will be a problem. And if we don't know which one is right, our tool will probably tell us you have around 98 degrees Celsius. And if instead we have over 105 degrees Celsius, this is not a rounding error anymore, but this is something that can lead to severe overheating problems in your final vehicle, so it should be avoided. And how can it be avoided? Well, first of all, you have to be aware that there might be a problem. You have to know that there is extrapolation occurring. And in our post-processing tool in KULI, we will give you an extrapolation warning. Other tools will most likely do very much the same. But people tend to disregard this because they say, oh, well, the temperature results looks good. Let's just move forward. And it is tempting, obviously, because you never want to replace a simulation result that's good with something that's problematic. But sooner or later, the reality will leap up on you, and because physics just cannot be cheated. Let me give you a second example again. So this is the pressure drop. This curve here on the left-hand side represents the pressure drop and the heat transfer in a tube. So we have a tube or a duct where coolant is flowing inside, And this could be, for example, a cooling duct inside a battery pack, for example. And depending on the flow rate of the coolant, you will have better or worse heat transfer. And there is a big difference whether you have low flow rates, where probably the flow inside the duct is laminar, and situations with higher flow rates where the flow inside the duct is turbulent. All of them will then, via this formula, give you a heat transfer coefficient. But if, for example, you have laminar flow, but you are applying the formula for the turbulent case, you will overestimate the heat transfer. If, on the other hand, you just extrapolate the laminar flow to an area where it's turbulent, you will completely underestimate the heat transfer. And both is not good, and both can be severe. In this case, we are over or underestimating our heat transfer coefficient by a factor 10. And this will, of course, lead to completely ridiculous tube designs, heat exchanger layout, whatever. And again, probably when you are used to this kind of topics, this will not happen to you. Or probably your tool will will prevent you from doing this because this functionality is built in. But there might be situations, maybe not so obvious situations, where you get some, where you have to model something, you're really looking in the internet for some formula, getting increasingly desperate just to find some straw that you can cling to that allows you to model a certain behavior. And when you find one, you do not check the validity area. And it has also happened to me. Sooner than you think, you can run in a situation where you are inadvertently extrapolating your model totally. And you can be lucky and it will never come up, but you can be unlucky and it causes severe problems. So model extrapolation is one issue, but also, of course, extrapolation of your test data. So how to summarize? Always check if extrapolation occurs. It's that simple. Of course, your simulation tool will help you with this. KULI definitely does. Others do as well, I would expect. And avoid extrapolation if possible. Of course, I'm not saying that extrapolation is a problem per se and always. There can be situations where you just do not have more information than what you have at hand. And in this case, you need to extrapolate. Maybe if extrapolation is just by a few % outside your tested area, it will be okay. It will be reasonable. Sometimes you will even have to go further out and just do an intelligent guess. But then at least you have to be aware that with the assumptions that you make, also your simulation results will be nothing more but an intelligent guess. They are probably better than nothing, but they are certainly not the truth. So if you must extrapolate, be careful and always check the plausibility. Deadly sin number 3, unnecessary complexity. I think the picture on the left-hand side once again shows it all. So once you get used to working with your simulation tool, once you become an expert, once you know how your tool works and you understand all the details, it will be very, very tempting to set up very elaborate models and just enjoy the level of detail that you have implemented and the pure beauty of it from an engineering point of view. But you shall also find beauty in simplicity, especially when complexity does not bring you benefit, as shows the next example. So this is a cooling system for a battery electric vehicle. So nothing very much fancy here. We have basically two branches of our cooling system. One branch which is for battery cooling, which is mostly cooled by a chiller because the temperature usually wants to have relatively cool coolant temperatures, maybe around 30 degrees Celsius, 25 degrees Celsius maybe. On the other hand, we have a second loop on the top side, which is for the powertrain cooling. Motors and electronics, they can live with higher temperature levels. They probably also will not be cooled by the AC system, but by a radiator instead. We have two coolant loops with two different temperature levels, so we want to run them probably separately. But in winter conditions, it can also be useful to use some warm coolant from the powertrain to heat up your battery. This is something that is modeled in several vehicles nowadays. I think one of the first who did this was the Tesla S. And this beauty here on the right-hand side, this is what I just slightly ironically called my favorite rotary valve. So I'm obviously in love with this component because I've modeled it with a very high level of detail. I've modeled all the different diameters of the inlets, the bends the coolant makes in the ducts leading into the valve. The interior of the valve is modeled with a very high level of detail, and for sure this will give us a very faithful reproduction of the mass flow, of the coolant mass flow distribution in our cooling system. And yeah, as I mentioned, this is the rest of the system, but nobody really cares about this when you have this beautiful, beautiful rotary valve, right? Wrong. The problem, of course, is the mass flow distribution in the ducts will not be influenced by the rotary valve. The question how much coolant flows through one branch and in through the other one is, of course, also heavily influenced by how much pressure loss occurs in the rest of the cooling system. So, as you can see, we have not modeled any ducts here in the rest of the cooling system. We just modeled some pressure drop of the components. Probably even that is not very accurate. We have pumps inside there, but it really lacks a lot of detail outside here. And it might be that your task in a project is to focus on the rotary valve, but still, without the level of detail in the rest of the cooling system, you will not be able to make any reasonable predictions, even if you add more levels of detail to your rotary valve simulation model. So, accordingly, this detailed valve here brings no benefit. It's just additional effort to set up. It's just an additional potential source for errors. Each of these components has some test data inside or some geometry data inside. Doing things wrong here, for example, extrapolation, it will just add additional problems. I'm not saying that you shouldn't do detailed models, but you should always validate if they make sense for your specific application and if they match the level of detail of the rest of your system. And if they don't do it. So, as a summary, let me say this. The accuracy of different parts of your model should always fit together. Doesn't make sense if it doesn't. Different parts can have different levels of detail, but you have to think about whether how they interact and whether they have adverse effects on each other. If they don't, it's perfectly okay. If it isn't, you probably should think again. And then, of course, avoid unnecessary details. Moving on to the next point, refusing help. This is something that I think even small children learn very early, that they can say, I can do it on my own, I can walk on my own, I can eat on my own, I can run my simulation model on my own. But sometimes it's not clever, because it's always better if you work together with some colleagues and let them double check your results. It's not about who is better, it's about getting the right results at the end of the day. So didn't find much statistical data on engineering simulation. What I did find, though, is some statistical data on software development. And a study from the University of Cambridge says that software developers on average spend almost 50% of the time with debugging. And this means you set up a model and then you spend time looking for the mistakes that you made. In our case, when we do some simulation, I mean, this is probably not the case when we're doing just a routine task. When you're always simulating the similar type of cooling systems or the similar type of components in your job, and you have standard processes, probably that's not so important for you. But ever now and then something new comes along, and then you will probably spend some time with trial and error to find a suitable methodology. You will then implement this in your simulation tool. You will probably not do software programming, but you will rather do some work with a graphical user interface, for example. You will still need to implement it, and you will still need to make some logical connections. Then you will debug. And when you have debugged, when it runs, then you still have to check if the results are reasonable and plausible. And if they're not, then you're back to the start and find some new methodology. And all of this costs a lot of time. And this is why I'm fairly convinced that these 50% for software developers are probably similar in engineering applications as well, at least when we are in uncharted territory where we do not have standard processes. So what we want to do, obviously, we want to minimize the effort for one, for trial and error, for three, for debug, and for the loops. And experience tells that colleagues, of course, can help you with this. So how can we reduce debugging overhead? The first point is not even talking to colleagues, probably, but just use simulation models that have already been validated as starting points. Do not always start from scratch. And if you do not have these simulation models available, maybe some of your colleagues have. So again, talk to them. Communication really helps a lot in most parts of life. And if they don't have anything, for example, for your software tool, for our software tool, we do have a library available on our homepage. Look up such libraries, whether there are some modeling templates. Again, these templates, they will be validated, and they can save you some gray hair. Then look for input on how to model specific topics. So if there are no pre-existing models, discuss your methodology with others before you implement it. Ask colleagues, talk to them, talk to your software support, because at least in case of our tool, we are not only telling you where to click in your tool, but we are always really happy and excited if we get some interesting engineering questions. We are engineers ourselves. We like solving problems. Contact us, and we will help you with that. And you could probably also look up your software manual or software homepage for topics like this. And if you really are in the unlucky situation that you have reached a dead end, do not dig in. This only leads to despair and costs a lot of time. Again, talk to your colleagues, talk to software support, explain your problems to someone else. My experience is, and I guess you have made similar experience, usually when you just explain your problem to someone, you will probably find the solution, because verbalizing your thoughts makes them more structured, and this can be just a small nudge in the right direction that will help you to solve the problem on your own. But again, you need to talk to someone. Don't dig in. I can do it on my own. Might be a good strategy for a toddler, but as an adult engineer, it can be very, very, very expensive. But I don't want to point my fingers on someone. I've been there myself. Probably everyone has. All right. Number 5. Ignore warnings. Don't do that. Or in other words, you shall listen to your simulation software. It will not always be telling you the complete truth, but it will give you very, very clear warning signs. And these warning signs could be, for example, your simulation model converges unusually slow, probably painstakingly so. This can be a problem. Probably it is okay, but it's definitely worth to check. You will not get a full convergence of some transient time steps. You're probably simulating a complete draft cycle, and just in a couple of seconds, there are some issues. The results overall will probably look quite okay, but these small issues, you should not outright neglect them. Always check. There can be a larger problem hiding behind them. There might be warning messages in your simulation log. There might be unreasonable results in unimportant parts of your model, but the important ones are okay. The question is, just because the important ones look okay, probably there is some interaction with these unimportant parts, and it's always worth checking. In the end, probably everything is okay, but please always check. Then a very nice, or actually a very sad example. Probably some of you know this. In 1999, a Mars climate orbiter was sent by NASA to Mars to investigate the climate there. They spent literally millions and millions and millions of dollars in this project for development, for launch, for operations, and in the end, it burned up in the Martian atmosphere just upon arrival, and it was lost. Millions and millions and millions of dollars lost. Then, of course, they started an investigation what went wrong, and they found out that this was a collaboration between American and European engineers, and they failed to convert units from English to metric. Something so trivial, and it led to losing millions and millions and millions of dollars and lots of work and hard blood. So always check your units. Always make sure that if your simulation tool supports using units, use them. It can be tempting to just save these 2 clicks to add the additional unit to your value. Don't do it. It's tempting, but it can lead to disaster. Just one example from our world in simulation of thermal systems. Let's just assume we have an electric vehicle battery charger where we are simulating 50 amp charging. And here for the heat exchange area, so for the heat transfer from the charger to the coolant, we have assumed an area of 5.382. And whatever the unit is, obviously the guy who was doing the simulation knew what he was entering there. The resulting temperature level is quite okay. It's only 32 degrees Celsius. That's just nice. That's not a problem. If we now become more bold and increase the charging current to 200 amps, so something for fast charging, we still get 64.3 degrees Celsius, which is still quite okay. It's not a big deal here, right? Wrong. The problem is that what was entered here as 5.382 actually were square feet. And this means, as we did not specify the unit, the simulation tool was assuming that this is SI units. And it just assumed that this is an area of 5.382 square meters. So obviously we have a huge heat transfer area here. But in reality, if we add the square feet value here, then instead we end up with 0.5 square meters. And the result is that the temperature level is now at 200 degrees Celsius. And I would say that we are now approaching temperature levels where probably a Martian probe might burn up, but we definitely do not want to have these temperature levels in your cooling system. Okay. Moving on to the summary. Always specify your units. It is important. Missing units might be misinterpreted, either by your simulation tool or by other engineers. Both is equally bad. Many simulation tools, including our software, they support unit usage. It's really just a click and everything will be fine. Problems will become much more obvious when you use units, and especially if you work in teams which cooperate between US and Europe, for example. It's imperative to use the units. Everything else will lead to problems sooner or later. And finally, the last point, wanting too much. So let's say, in a way, greed. And I've titled this in the beginning, there was a heat exchange. And what I mean by this is a very simple thing. Really a very simple recommendation. Do not start with the full complexity in your simulation model. Always increase the complexity step by step. So, and always test and validate your simulations model before you take the next step. I'm from Austria. In Austria, we have a lot of mountains, and when you're climbing in mountains, one of the basic things is always secure that you have a safe step before you make the next one. And it's just the same in simulation engineering. So in this example, we have a system where we have a battery cooling loop, an e-drive cooling loop, and an air conditioning loop. And we can model each of them separately, and we can validate each of them separately. So this is what we definitely should do before we assemble them. And when we have assembled them, then the next question is, what about the controls? Because the control system is something that is usually just as complex as the physical representation of your cooling system itself. A lot of things can go wrong there. So before you start fiddling with the controls, use some dummy controls that produce easily reproducible values and check whether your simulation model performs as it should. And then, and only then, you should take the final step to first split up your controls and test the controls each by itself, and then assemble them to a complete vehicle model, including the complete controls. Again, this is something that seems to be very obvious, but especially in our support activities, we frequently see people committing just this sin, especially people who are not so used to simulation. They sit at their computers, they create the mother of all simulation models in 14 days of intensive work, and then they click the simulation button, the go button for the first time, and nothing works. And as you can imagine, finding the needle in the haystack, or probably the needles, because for sure they have made more than one mistake, is just a lot of trouble. And usually they try to fix this then for maybe another 3 or 4 days, and after that they're so frustrated that they either never simulate again, or they just throw away the model and start over. And this is something that can be avoided by taking individual steps. So, as said before, if you can use previously used and validated models, they are an excellent starting point. Do that. Increase this complexity step by step, and also, especially when you are a beginner, don't do this. Talk to your colleagues and listen to recommendations. So we're now in the end, and let me just reiterate on these 7 deadly sins, and let's just summarize them once again before we get to the general discussion part. So, no data validation, very bad. Extrapolation without being aware that you're actually extrapolating, don't do that. Unnecessary complexity, it will cause a lot of trouble. Refusing help, not a good idea. Ignoring warnings can go well, can lead to disaster. Neglecting unit most certainly will lead to disaster. And wanting too much is not a good idea as well. So with that, I'm finished with my part, and I really would like to hear from you, maybe some questions, or maybe also if you can share some experiences from your side. We are very happy for that. So Rolf, I think you are checking the questions. Do we have open questions that you haven't been able to answer so far in the chat function?
Yes, there are some questions. So first, we have had, maybe, or some of you have had some problems with the audio or video connection. Sorry for that. But there is a good news. So you will get a link from Natalie from IMechE in a short time for the recorded video, and then you can take a look on this video. I think it will be published on YouTube, and for sure you will get the link after the session. So then we have one question: what software packages do you have used for the simulation, Christian?
Yeah, so in this example, I have mostly referred to our simulation tool KULI, which is a 1D simulation tool for thermal management simulation in cooling systems. But it also covers basically basic driving simulation, HVAC topics, passenger comfort in the cabin, and so on. So it's a general, all-purpose, very comprehensive thermal management simulation tool.
Thank you so much. So next question. So what is an example of the biggest sins you have done in the past year or month?
Very, very good question. Probably from time to time digging in. That when something just doesn't work and you don't talk to colleagues and you do not accept that it doesn't work, because it feels like it's just one little step further. And as they say, the road to hell is paved with good intentions. Probably it was something like this, yeah.
Okay, so next question. Do you have any recommendations for how we should bring together simulation and test data for comparison?
Yeah, I do have some recommendations, actually. I mean, it's always a good idea to put them side by side, really. So depending on what your simulation tool supports, the way that usually always works is just by getting everything into Excel, because everyone has Microsoft Excel, and I'm not making advertisements for them, but that's just the way it is. And you can if you can copy and paste your data in there, then this might really help. I mean, people are visual, so it's much easier to comprehend what's going on if you have the same data in one chart. So that's definitely a recommendation. In several simulation tools, like also, for example, in KULI, it is possible to import Excel data also into our proprietary post-processing tool. But that's just another way to do it, basically, even if that's not possible. But the general recommendation is visualize. That's definitely an important point.
Yeah, another question which we have got is, must all simulations still end up with a test of a prototype? Is there a risk of making the simulations to fit the physical system?
Good question. So I think at least in automotive industry, usually the simulations are a part of the development process, and obviously there will be prototypes, and it does make sense to iterate also your simulation models after the first prototype test results come in, because at the end of the day, it doesn't really matter whose fault it is that these the simulation results and the test data diverge in some points. You should make them fit, because only then you can make predictions for future developments. So, for example, let's just say you have a perfectly precise simulation model, but in the final prototype, one additional band was installed in one of the ducts, or some component from a different supplier was chosen. Then obviously your simulation model is correct, but it will not match the prototype testing. And if you want to build a second and a third prototype, of course, it is highly beneficial if you can make predictions based on your simulation model. So at least in automotive engineering, I would always recommend that simulation is not a step which is finished and then never looked again, but rather a process that runs continuously in parallel to the complete development work, and is always checked with testing, and always calibrated to testing, so that these two branches do not move too far apart from each other.
Okay, thanks for the answer, Christian. So the next question is, are you able to model transient organic Rankine cycle systems which includes phase change heat exchangers?
Yes, we do.
Okay, let's see.
So actually, these Rankine cycles, they were quite a big thing a couple of years ago. That's when we also did a lot of work on that. It has become a little bit more quiet over the last years, but I can imagine that there are some applications where they might get very interesting again. So yes, we definitely have this functionality.
I'm looking for some new ones. So what is the ideal way one could simulate a theoretical problem without any test data for validation?
If someone knows, please tell me, because That's usually the expectation that we get from our bosses and also sometimes from our customers. No, but seriously, I mean, yeah, of course it helps if you have some experience. Of course it helps if you have some reference data from previous projects. Well, you just have to make an intelligent guess. I mean, sometimes it really depends on how much data you have. Sometimes you should even question if you really need a complete simulation when you have very little data. Sometimes, and I'm being absolutely serious with this. Sometimes it makes more sense to take a pen and a paper and just do a very rough estimation on the paper. If you have very, very little data available, probably 2 or 3 calculations will get you just the same results than when you start up a computer and create a simulation model. And it will probably also help you not to lose the touch to what you're actually working on. But if you have a little bit of data, yes, well, experience helps, and especially having reference data helps. So if you're doing a lot of projects, always make sure that the experiences you make are not lost and that they can be used for subsequent projects.
All right, I think now another question in this regard. So in your experience, do you find that engineers believe simulations more than experimental data?
Generally, I wouldn't say so. I think everyone who's in the business for some time has a healthy respect for testing. I mean, we experience a lot of things that can go wrong in testing as well, and we experience a lot of problems that can go wrong in simulation. I wouldn't play one against the other. I think in a development process we always need both. You know, I mean, we sometimes have management circles getting the bright idea that they do completely virtual development because this, of course, can save you a lot of cost. Tests are always very expensive, so let's just set up the perfect simulation process and then skip these tests altogether. The world doesn't work this way. So in my experience, the really important thing is to get a stable process which ensures that you get the best from both worlds and that you also talk to each other. So simulation engineers and test engineers should talk to each other. Simulation engineers should be sometimes present at the tests, and it also doesn't harm if sometimes a test engineer will be able to at least work with the simulation model just to probably validate immediately his sensor readings at the test bench. So some OEMs, they are doing just this, and they have made very good experiences with this, and this is what I can only recommend. So I do not blindly trust tests, but I also do not blindly trust simulation results, and you always need both.
Okay, then I have another question to validation. So the question is, I was taught to validate the simulation using hand calculations. That shows not always seem practical in complex simulations. Is this validation method still relevant with modern complex software and models?
It probably is. I mean, in the end, I just mentioned, take a close look at your simulation model and check whether it's plausible. That's even lower level than doing some calculations by hand on a sheet of paper. I mean, it all boils down to experience and to your feeling. I mean, it's very hard to quantify this, but the longer you work on some kind of problems, when you see some results, you will get a strange feeling about them, or you will have the feeling that they are probably okay. And of course, there are exceptions to this rule. So sometimes yes, it can make sense to use just a sheet of paper and do some quick evaluation. The advantage of this is that you can even do this live in a meeting while someone is presenting results. You just don't have to open up your laptop computer if this is really just to get the order of magnitude right. And sometimes when the order of magnitude is not right, you can just show that something is terribly wrong with some simple calculations. And in this case, such a simple calculation can save a lot of time, and also it will earn you a bit of respect with your colleagues probably when you are the magician who just does some calculation on a sheet of paper and finds out what's wrong. But that's not why we do it. We're not doing this for effect, of course. I'm just joking. Yeah, but I think there are applications where it can make sense. In complete systems, of course, well, obviously, this cannot replace some more detailed calculation.
Okay, thank you. So I think I have one last question. I have a lot more, but we cannot answer in the time because we have only this 1 hour time, so we are limited in our answering time. If you have any additional questions, please send us to the questions to our email address kuli.support.mpt@magna.com. We can, of course, answer your questions, baby. But my last question to you, Christian, for today, what is the biggest challenge in carrying out engineering simulation?
Well, I would say usually for me in many projects is getting the data, because sometimes models nowadays are very refined, but they still need a lot of data because reality is complex. And as the very first slide, one of the very first slides that I showed says, when you enter garbage, you will only get garbage out. So probably getting good and plausible data is the most important thing. And for this, I think it's very important that OEMs and suppliers work closely together. And I think, yeah, that's probably what we will need also in the future with more and more complex systems. So probably that's some nice last words. Let me maybe just add one more thing. Yes, if you have open questions, just write us an email. And we, of course, also very open to have one-to-one phone calls or web calls to you if there are some large topics that we need to discuss. We do this because my experience is that whenever we talk to someone about such topics, we also learn a bit for ourselves. So ideally, this leads to a win-win situation. So just contact us and we will help you in any way we can. Thank you very much.
So thanks very much and bye-bye. Have a nice day. And if you want to get the slides, please write us an email. If you want to review the webinar, please follow the link which you get in a short time from the IMechE.